So now I want to connect the idea of the change of entropy in the universe to another concept we've looked at quite a bit, which is the concept of equilibrium. And the reason we want to connect these two ideas is because entropy allows us to predict whether a reaction is going to be spontaneous or not, which requires us to calculate the change in the value of entropy. And if that number is positive, we know that the reaction is going to go from reactants towards the product. But eventually that reaction will stop when it reaches equilibrium. So the question then becomes, what happened to the change in entropy when a reaction is at equilibrium? It's pretty clear that the change of entropy when a reaction is at equilibrium should be zero. That's because at equilibrium, the reaction is no longer going to go towards a specific direction. The reaction is finished per the definition that we don't see any change in the concentration of reactants and products over time. So if the reaction is done, that means it's not going to go whether towards the product side or the reactant side. So if we calculate the delta S of the universe for a reaction at equilibrium, we should get a value equal to zero because it's going to tell us that we're not going to go to a particular direction. This is how the two concepts of entropy and equilibrium are connected together. The way you want to think about it as you go through a reaction is described here, but I'm going to draw it out for you in this graph. So imagine that we have a plot where x-axis is time and the y-axis is entropy of the universe value of your species. So we kind of split this plot into three different parts. At the beginning of the reaction, the entropy of the reactant is pretty low and the entropy of the product is pretty high. So if we just calculate the change in entropy, which is going to be the product minus the reactant, we get the delta S of the universe in this case. That number is going to be positive. And so that tells us that the reaction is going to go towards the product side. If we let the reaction go for some time, some of the reactant is going to convert to product. And so at that point, the reaction has gone quite a bit. So the mixture of molecules is no longer the same as the very beginning. And so at that point, you're going to have a little bit of a closer distance between that reactant and product mixture. Okay, the delta S of the universe is still going to be positive, but it's just going to be a little closer together. Eventually, when you reach equilibrium, the two numbers are going to be the same. So when your delta S is equal to zero, then there's really no reason for the reaction to go any more at that point. It's just done. Okay, delta S tells us that there's no directionality to this reaction because the delta S is zero. Okay, so that's kind of how you want to think about a reaction as it's progressing. Initially, you start with a delta S value that is pretty positive, and then eventually it gets closer and closer to zero, and eventually when it reaches zero, that's when you know your reaction is done. And that's what I describe in this part of the notes here. So one way you can tell that a reaction is at equilibrium is just by calculating its delta S. If you get a delta S of the universe equal to zero, then you know that your reaction is at that point has reached equilibrium. And this becomes a useful thing to calculate, for example, like if you want to know the temperature for a reaction when it's boiling or freezing, which are changes of state. Changes of state occur when two states are in equilibrium with each other. You can find those boiling points and freezing points by letting your delta S of system equal to delta S of the surroundings. We know that at that point, those two numbers are equal because your delta S of the universe has to be zero because it's an equilibrium condition. Let's work out a problem here that illustrates this idea of the value of delta S universe at equilibrium. I'm being asked to calculate the delta S of the universe for the vaporization and condensation of 1 mole of water at 100 degrees Celsius. Now we know that 100 degrees Celsius, just from prior knowledge, is the boiling point of liquid water, right? So at that temperature, we know that liquid and gas water are at equilibrium with each other. So the point of this question is just to show you that in theory, if we were to calculate the delta S of the universe, we should get a number that is zero or pretty close to zero. And so that's what we're going to do here. If we want delta S of universe, we're going to need delta S of the system and delta S of the surroundings, right? So we can calculate that if we have our thermodynamic value. So as I mentioned earlier, you can find it using that same table that we used before for entropy. So entropy is the purple column here, and then delta H formation is the pink column there. And to calculate the delta S of the system, given the symbol, all you need is take the number of moles of your product times the absolute entropy value of your product minus the number of moles of the reactant times the absolute entropy value of the reactant. Of course, to do that, we're going to need to write our reaction out. Our reaction is liquid going to gas because that's vaporization. And so this is the actual equation to calculate delta S of the reaction. I found those numbers there in that table for both of these guys. Again, the reason this is 1 is because the coefficient is 1, right, for both of those species. And so I found that my change in the entropy of the system is positive 1.915 joules per Kelvin. Now I need to calculate my delta S of the surrounding, which remember is this formula, negative delta H of the system divided by temperature of the surrounding. The delta H of the system I can calculate using my enthalpy of formation value. So it's the same type of formula except that you use a different thermodynamic value, so products minus reactants in this case. I found those numbers in my table and I end up getting positive 44.012 kilojoules for the enthalpy change. The change in entropy of the surrounding is negative, don't forget that negative sign, of the delta H of the system divided by the temperature of the surrounding. Those are the numbers, so I end up getting negative 117.995 joules per Kelvin. To get my delta S of the universe, I'm going to add the two numbers that I found, the delta S and the delta S of the surrounding. And when I get the two numbers, you can see how they're really close together. One of them is 118.9, the other one is 117.9 or almost 118. So pretty much when you add the two of them together, you get a number that's pretty close to zero. The reason it's not exactly zero is just because of experimental measurements. You know, some of these measurements are not necessarily done at the appropriate temperature where the values are supposed to be done, right? And so we're kind of making a little assumption here about the numbers not changing at different temperatures. It is pointing to the fact that when a reaction is at equilibrium, its delta S of the universe would be equal to zero. And you can see how this number could be useful. So for example, if I want to calculate the boiling point of water, let's say I don't know that water boils at 373 kelvins or 100 Celsius, all I need to do is just calculate the delta S of the reaction, which is 118.915. Since delta S of the universe is zero, that means that the value of the delta S of the system should be the negative of delta S of the surrounding. And since I know this is equal to negative delta H over T, you can see how knowing this number and knowing the delta H allows me to calculate the equilibrium temperature. Okay, so anytime I need the temperature of a particular phase change, I can calculate it if I have access to these thermodynamic values of entropy and enthalpy. Now I want to point out something that we had observed early on in the beginning of this topic on thermodynamics, and that is about entropy change and delta H. Remember that at the beginning, we kind of looked at delta H as perhaps the quantity that will tell us whether a reaction is going to be spontaneous or not. But then we concluded that that's not really the case. However, I did say at that point that if we look at all the reactions that are possible in the universe of chemical reactions, we notice that exothermic reactions, more of them tend to be spontaneous, whereas endothermic reactions, more of them tend to be non-spontaneous. Now, we didn't really explain why at that point, but now we can. So keep in mind that there's two components that tells you spontaneity, right? And that is the components that we found in delta S of universe, which is the delta S of the system and then the delta S of the surrounding. And delta S of the system we can calculate using those molar entropy values. Delta S of surrounding we figured out is equal to the negative of the delta H of the system over temperature. And so that tells us that when our delta H is negative, exothermic reaction, our delta S is going to be positive, whereas when our delta H is positive, which means endothermic reaction, our delta S of surrounding is going to be negative. Now, remember the criteria for spontaneity. We want the delta S of the universe to be positive. So that means that we want either both numbers to be positive or at least one of the numbers to be positive, right? In this case, maybe the delta S of surrounding, if the delta S of the system is negative. So we want, in the end, our number to be positive for this reaction spontaneous. So can we explain why more exothermic reaction is spontaneous compared to endothermic reaction? Yes, we can, because notice that just by virtue of this relationship between delta H of the system and delta S of surrounding, we see that exothermic reactions automatically have a positive delta S of surrounding. So that means that at least one of these two numbers is already positive. And so it makes it easier for this delta S of the universe to be positive, which means it makes it easier for the reaction to be spontaneous. Whereas if you have an endothermic reaction, delta H is positive, your delta S of surrounding is going to be negative. So one of these numbers is already negative, which is unfavorable for spontaneous. So therefore, the delta S of the system now has to overcome the value of delta S of surrounding in order for the two numbers to be positive. And so that's really the reason why when we look at all reactions, exothermic reactions are more likely to be spontaneous than endothermic reactions.